Okay, everybody loves synthesis, and this is really where things start to get challenging. It's when we get into the alkynes chapter, because now you really do have, instead of having 12 or 13 reactions, now you've jumped up to having 25 or 30 reactions, and you got to be able to use them all to accomplish a synthesis task. And so what I wanted to do is go ahead and show that as show some of these possible synthesis solutions to these problems, and use this idea that we're going to think backwards. So this is it's not the only way to solve synthesis problems, this idea of retrosynthetic analysis, but it certainly works. And if you get enough practice at it, you start to come up with the right answers every time. Now, with that being said, there's more than one way to do a synthesis problem. And I'll show you on the second one, there's going to be two completely separate ways to possibly do it. And is there one answer that's better than another? In organic chemistry class? Probably not. Now, in real life, sure, one of those reactions sequences is going to be easier to do than the other. And so that's a whole nother question. Okay, so let's take a look at the first one. So let's think backwards. What do we have here? What's the functional group that we have here? It's a carboxylic acid. And so that means that I've got very few reactions that I know of that can form carboxylic acid. And really the only one that I know of is ozonolysis of an alkyne. Okay, let's think about other things that are going on with this. I've got a carboxylic acid and I've got 1, 2, 3, 4 carbons. How many carbons do I have in my starting material? It looks like I have 5. And so that's also telling me that I'm going to use ozonolysis because I'm missing a carbon. And so let's just go ahead and do this retrosynthetic analysis. Let's think back one step. What would this have been? Well, if I were going to make a carboxylic acid here, then I would have had to have a 6-carbon alkyne. And that 6-carbon alkyne would have split the triple bond there and formed a carboxylic acid. And so, of course, the reagents to do that are O3 and water. That it's usually a 2-step reaction. So let me go ahead and label that. Okay, and so now I want to figure out, how do I get to this alkyne? Well, the only thing I can think of for making alkynes is I can either use alkylation with an alkanide ion, but the thing about using alkylation with an alkanide ion is that it forms carbon-carbon double bonds. I start off with 1, 2, 3, 4, 5 carbons. I end up with 4 carbons, and in order to end up with 4 carbons, I had to cleave off one of those carbons, and I still have 5. So at this point, I've got all the carbons that I need. I don't need to add or remove any, so that isn't an option. Alkylation with an alkanide ion isn't an option. The only other way that I know how to make alkynes is through reduction. So I could excuse me, not reduction, but elimination. I could do an elimination of Br and Br here with excess sodium amide in my first step, and in my second step I would need to reprotonate that with water. That'll do that, so no problems there. And then what about this? Let me continue to think backwards. What can I do? Can I get a Br2 added across a double bond? Well, of course, if we go back to our alkene chapter, we could just do a Br2 reaction there. So then let's put it all together. What are the steps? Br2, excess sodium amide, water, then O3, and then water again. And so that's the synthesis solution for that reaction. Okay, what about this one? What about the next one? Let's take a look at that one. Oh, I got a lot of stuff to erase here. All right, what can we do here? How many carbons do I start with? Let's think backwards. 2, but I end up with 3. What is the functional group that I have? I have a carbonyl group. Okay, so there are some ways to make carbonyl groups. I know two ways. I can make a carbonyl through ozonolysis, uh, but that's with an alkene. And the other way that I can do it is I can do an I can do hydration of an alkyne. Now, if I do hydration of an alkyne, I have to think about, is it Markovnikov or anti-Markovnikov? This one's terminal, so it's clearly anti-Markovnikov. So this is the one where I said, look, there's going to be multiple ways to skin the old synthetic cat, and so this is one of those situations. And so I'm going to actually show you both methods. One method would involve having a double bond here, and so actually having a carbon. And so how would I do this? How would I actually have the carbon? This would be O3 and DMS. That would make this reaction take place. Okay, how does this work? Let's think. Well, I start off with an alkyne, and I need to get to an alkene. Well, I can do that with Lindlar's catalyst if I have this, H2 and Lindlar. Okay, now that I've done H2 and Lindlar, how do I make this thing? Well, I can, if I take this and I react it with sodium amide, it will turn it into an alkynide ion. And then that alkynide ion could react with a 2-carbon alkyl halide, and then I would make the reagent that I have with star. So that's certainly one possibility. One possibility would be sodium amide, followed by ethyl bromide, followed by H2 Lindlar, followed by O3, and then finally DMS. So that's certainly one possibility. What would be the other possibility? Well, I can make this same 1, 2, 3, the carbonyl group at the terminal position by hydrating an alkyne. But this would be anti-Markovnikov, so I would need to have I would need to do oxymercuration, not oxymercuration, I need to do hydroboration oxidation. Okay, so how could I make this alkyne? Well, I start off with a 2-carbon alkyne, and so I need to add 1 carbon to it. So I can, if I, again, sodium amide, and instead of ethyl bromide, I use methyl bromide. I'll add the 1 carbon that I need. So another possible solution would be sodium amide, methyl bromide, and then hydroboration oxidation. Okay, which answer is correct? Well, they're both correct. Which answer is more efficient? Well, the answer that's more efficient is this one. And the reason is that in this one, you have a carbon that disappears. And so you want to, generally you want to be as efficient as you can with your carbons. And so if you don't have to get rid of one, then don't. So we bring in 2 carbons in this step, but then we get rid of one of them later on down the road. We're not being efficient with our carbons. Okay, so let's keep going then with what's the next reaction? The next reaction clearly has 1, 2, 3, 4 carbons, and I'm going to add some carbons along to that as well. Okay, and so let's just think about this one from a retrosynthetic standpoint? Well, I sort of am asking the same question that I did before. How could I make this structure? Well, I could make this structure, just like we said before, I could make it from either O3 or in DMS by getting rid of one of the carbons and making it into a carbonyl group, or I can do anti-Markovnikov hydroboration oxidation. So for the same reason that we did before, let's go ahead and start off with hydroboration oxidation, because that's going to be more carbon efficient. Okay, well, how could I make this structure? Well, this one's an interesting structure. It's an alkene. So I have several options for making alkenes. And the question is how do you know which alkene to do that with? And I'm going to go ahead and have to back up, because this is improper, right? It's not actually an alkene here. I did this hydroboration oxidation is hydration of an alkyne. This makes a little bit more sense, and I apologize for any confusion. Well, how do I do this? Well, I can make this by adding an alkynide ion to an alkyl halide. And so this is where I got my extra carbon from. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Here's the 5 and the 6 that I brought into the reaction. So I still have 1, 2, 3, 4. Yep, let me correct this. And I'm bringing in 2 extra into the reaction. So count your carbons. Okay, so how can I make this guy? Well, this is an anti-Markovnikov addition of Br, so it's HBr and ROOR. So the synthesis to this one is HBr, ROOR, alkynide, and then hydroboration oxidation. Okay, that's synthesis.